Right now, gravity is pulling you down. You can feel it. You're sitting in that chair, and this enormous ball of rock and iron beneath you is reaching up through the floor and hauling you toward its center. Every single second, gravity grabs you. It grabs the coffee in your cup. It yanks the bird off the branch. It drags rain out of the sky. You've known this since you were 2 years old, the first time you toppled over and planted your face on the ground. Gravity pulls things down. It's the most obvious force in the entire universe, and it's completely wrong. Not slightly wrong, not needs a small correction wrong. Wrong. The whole picture, this idea of a force called gravity reaching out and tugging you toward the earth, is a fiction. A remarkably useful fiction. I'll give it that. It got us to the moon. It predicted planetary orbits. It works beautifully for nearly every calculation you'd ever care to do. But it is not what is actually happening. What is actually happening is so strange, so thoroughly upside down from everything you think you know, that when I tell you, your first instinct will be that I'm pulling your leg. I'm not. Nature has been pulling your leg every single day of your life. So let's begin with what everybody believes, and let me show you why everybody believes it. Because the wrong idea is a genuinely magnificent idea. It held up for over 2 centuries. The sharpest minds in history used it, tested it, staked their reputations on it. I want you to feel how solid it seems before I dismantle it. Isaac Newton, sitting in England in the 1680s, figured out something spectacular. He realized that the force dragging an apple off a tree is the same force holding the moon in its orbit around the Earth. Same force, same law. The apple and the moon are doing the same thing. That was a staggering leap. Before Newton, people assumed the heavens ran by entirely different rules than the muddy ground underfoot. Stars moved one way, rocks moved another, and nobody connected them. Newton connected them. His law says this: every object in the universe pulls on every other object with a force that depends on their masses and the distance between them. Double the mass, double the force. Double the distance, the force drops to 1/4. Clean, simple, elegant. You can write it in one line, and from that one line, you can work out the motion of every planet, every moon, every comet arcing across the night sky. And it works. My God, does it work? Edmund Halley used Newton's law to predict that a particular comet would swing back around in 1758. He was already dead by then, but the comet returned right on schedule, appearing in the sky within weeks of where he said it would be. Imagine the feeling. A dead man's calculation, vindicated by the heavens. When astronomers noticed that Uranus wasn't quite following the path Newton's equations demanded, they didn't throw out the law. They reasoned there must be another planet out there, one nobody had spotted yet, pulling Uranus off course. 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently sat down and calculated where that hidden planet had to be. They told the telescope operators, "Point here." The astronomers pointed, and there it was. Neptune, a whole new world, sitting exactly where Newton's gravity said it must be. Le Verrier didn't discover Neptune by looking through a telescope. He discovered it by writing on paper with a pen. That is the kind of success that makes you trust a theory with your life. It didn't stop there. The tides, Newton explained them, the moon tugging unequally on Earth's oceans, stronger on the near side, weaker on the far, raising 2 great bulges of water that slosh around as the planet spins. The shape of the Earth. Newton explained that too. Why it bulges at the equator, the spin flinging matter outward while gravity tries to pull it into a perfect ball, the compromise being an oblate spheroid, fatter in the middle, exactly as he calculated. Cannonball trajectories, satellite paths, the way a car hugs a curve, all of it flows from that one little law. So here's Newton's picture. The Earth has mass, you have mass, and across the space between you, the Earth's gravity reaches out, grabs you, and pulls you toward its center. The floor gets in the way so you don't fall through, but the force is always there. You feel it as weight. Everything in your daily experience confirms this. You drop something, it falls. You jump, you come back down, force pulling down, case closed, except it isn't closed. There's a crack in this beautiful picture, and the crack was there from the very beginning. Newton himself knew about it, and it bothered him terribly. Here it is. In Newton's law, Gravity acts instantaneously across any distance. The sun pulls on the Earth right now, this instant, across 93 million miles of empty space, with no delay. If the sun vanished this second, Newton's equation says the Earth would immediately fly off in a straight line. Not 8 minutes later when the light disappears, but immediately, faster than light. Newton despised this. He wrote in a letter that the idea of one body acting on another through a vacuum with nothing in between to carry the action was so absurd that he couldn't imagine any sensible person ever accepting it. He published the law anyway because it gave the right answers, but he never figured out how the force was transmitted. He said essentially, I'm giving you the mathematics. The mechanism someone else will have to sort out. For over 200 years, nobody did. The force seemed to work by pure magic, reaching across empty space with no medium, no messenger, no explanation. People got comfortable with it. They stopped asking, but the crack was always there. There's another crack, subtler, and in some ways more important. Gravity has a peculiar property that no other force shares. Everything falls at the same rate. A hammer and a feather in a vacuum hit the ground at the same instant. Galileo worked this out by rolling balls down ramps. Apollo astronauts demonstrated it on the moon, dropping a hammer and a feather in the airless lunar landscape and watching them descend side by side. Now, why should everything fall at the same rate? In Newton's law, the gravitational force on an object is proportional to its mass. But the resistance of that object to being accelerated, its inertia, is also proportional to its mass. The mass appears in both parts of the equation and cancels out. The acceleration is always the same, regardless of what you're made of. Newton noticed this and treated it as a coincidence. Two completely different properties of matter, how hard gravity pulls and how hard it is to shove, just happen to be numerically identical for every substance ever tested to extraordinary precision. That's not a coincidence. That's a clue. And Einstein saw it. Einstein saw both cracks, the action at a distance and this perfect equivalence of gravitational and inertial mass, and he realized they were pointing at the same conclusion. Let me widen those cracks for you now. I want you to do a thought experiment. You're inside a sealed box, no windows. You're standing on the floor and you feel your normal weight pressing you down. You drop a ball, it falls. Everything feels exactly like standing on the surface of the Earth. Question: are you on the surface of the Earth? Maybe. But you could equally be in deep space, far from any planet, inside a rocket accelerating upward at exactly 9.8 meters per second squared. The engine is pushing the floor up into your feet. When you drop the ball isn't being pulled down at all. It's floating freely in space, and the floor is rushing up to meet it. From inside the box, you cannot tell the difference. No experiment, no instrument, no measurement will reveal whether you're sitting in a gravitational field or riding an accelerating rocket. None whatsoever. Now think about what that means. If gravity were a real force in the ordinary sense, like electricity, you should be able to detect it from inside. With electricity, you can build a detector. You can shield against electric fields. You can distinguish being pushed from being pulled. But with gravity, you can't. No detector, no trick separates the two situations. Gravity and acceleration are indistinguishable from the inside. This is Einstein's equivalence principle, and he called it the happiest thought of his life. Not his wedding, not the birth of his son. This idea, because he immediately saw what it implied, and what it implied was devastating for Newton. If gravity were a genuine force, you should be able to detect it, regardless of your state of motion. That's what forces do. They show up in your instruments. An electric field acting on a charged particle inside your box makes that particle drift. You can measure it, confirm it. But gravity affects everything identically. Every mass, every composition, every shape, all falling together. Double the mass of something. The gravitational pull doubles, sure. But the inertia doubles too, and the two effects cancel perfectly. Every single time, without exception. That's not an accident. That's nature whispering that gravity isn't the same kind of thing as the other forces. Einstein listened to that whisper. Now imagine you're in that same sealed box, but this time you're falling. Somebody has pushed you off a cliff, box and all, and you're plummeting. What do you feel inside? Nothing. You're weightless. The ball floats beside you. Your coffee drifts out of the cup in little wobbling spheres. A scale would read 0. Every effect of gravity has completely vanished. This isn't just a thought experiment. We've done it. Astronauts on the International Space Station float around, their hair drifting upward, water forming into blobs. People say, "Oh, that's because there's no gravity in space." Wrong. The station orbits about 400 kilometers up, where Earth's gravitational pull is still roughly 90% as strong as it is at the surface. Gravity is very much present. The astronauts float not because gravity disappeared, but because they're falling. The station is falling. They're all falling together in a great curving arc around the Earth. And when everything falls together at the same rate, you cannot detect any gravitational effect whatsoever. You've experienced this yourself briefly on a roller coaster as it tips over the top of a hill. That stomach-dropping sensation, that moment of lightness, that's weightlessness. You're in free fall for a few seconds, and for those few seconds, gravity ceases to exist as far as your body is concerned. Your inner ear registers zero acceleration. You feel free, literally, physically free. No force acting on you at all. Planes that fly parabolic arcs for training astronauts do the same thing, climbing steeply, then pushing over into a freefall arc for about 25 seconds. Inside the cabin, people float and do flips, playing with globs of water, and the plane is still deep within Earth's gravity, being pulled at 9.8 meters per second squared. Yet inside there's nothing to detect. Let that really settle in. When you fall freely, gravity vanishes. Not seems to vanish. Not is approximately gone. It is gone. No experiment inside the falling box can find it. And if you can't detect it, in what sense is it there? Compare this to any real force. If I push you sideways with my hand while you're falling, you'll feel that push. An electric field will deflect a charged particle inside your box, and instruments will record it. Real forces leave traces. Gravity in free fall leaves none. Now, someone perceptive in the audience will raise an objection. What about tidal forces? If you're falling toward the Earth in a large enough box, two balls on opposite sides will drift slowly toward each other, because they're both falling toward Earth's center, which is a slightly different direction for each one. You could detect that. So gravity isn't completely invisible in free fall, right? That's correct, and it's an important point. Tidal effects are real. They're the signature of genuine space-time curvature. If your box is large enough, objects at the top fall slightly slower than objects at the bottom, and objects on the sides drift together as they converge on the planet's center. These are the same effects that raise the ocean tides, the moon pulling slightly harder on the near side of Earth than the far side. But here's the key point. These effects are proportional to the size of the box and to how much the gravitational field varies from place to place. Make the box small enough, shorten the observation time enough, and the tidal effects shrink to nothing. In a small enough patch of space for a short enough time, free fall is perfectly, completely indistinguishable from the absence of gravity entirely. This is Einstein's equivalence principle stated more precisely. Locally, you can always make gravity disappear by falling freely. The tidal stuff only shows up when you compare distant points, when you look at how different regions of space relate to each other. And that, the relationship between neighboring regions, the way paths that start out parallel can converge or diverge, that is exactly what curvature means. A single ant on the surface of a basketball can't tell the surface is curved. It takes comparing paths, comparing directions, comparing neighbors to see the curvature. Space-time works the same way. So look at what we have. When you stand on the ground, you feel something. When you fall, you feel nothing. Newton says the something you feel is gravity pulling you down. But if gravity is truly a force, why does it completely vanish the instant you're in free fall? A real force doesn't behave that way. A real force shows up in your measurements. Gravity only shows up when something is blocking you from falling. Let me say that again, because it's the hinge on which everything turns. The only reason you feel gravity right now is that the ground is in your way. The ground is pushing you up. That's the force you feel. That's your weight. The chair pushes against you. The floor pushes against the chair. The Earth's surface accelerates you upward, away from the free fall path you'd naturally take. And here's Einstein's shattering insight. Falling freely isn't being pulled somewhere. Falling freely is doing nothing. Falling is the natural state. That's the big reversal. Newton says you're sitting still and gravity is a force dragging you down. Einstein says, if you want to know what natural unforced motion looks like, like. Watch the astronaut floating in the station. That is the natural state. The person in the chair, feeling pressed and weighted. That person is being accelerated. The ground is shoving you. You're the one under a force, not the falling apple. The falling apple is free. I know this sounds completely mad. How can sitting perfectly still in a chair be acceleration? You're not going anywhere, you're not speeding up. But Einstein isn't talking about acceleration through space in the ordinary sense. He's talking about acceleration through space-time. And to understand that, I need to tell you about curved space-time. I'll keep it as plain as I possibly can. Here's the gentlest way in. Forget the universe for a moment. Just think about the surface of the Earth, the two-dimensional skin of it. If you and a friend both start at the equator pointing due north and walk in perfectly straight lines, what happens? You converge. You draw closer together. By the time you reach the North Pole, you're standing on top of each other. Did some mysterious force pull you together? No. You both walked in straight lines, no turning whatsoever. But the surface you were walking on is curved, and on a curved surface, straight lines that start out parallel can converge. Space-time works the same way, except instead of a two-dimensional surface, it's four-dimensional, 3 of space and 1 of time. And instead of being curved by the geometry of a sphere, it's curved by the presence of mass and energy. The Earth's mass warps the space-time around it. Objects moving through that curved space-time follow the straightest possible paths, what physicists call geodesics. And here's the critical part. Everything is always moving through space-time. Even when you're sitting perfectly still in space, you're marching forward through time. You can't stop that, 1 second per second, relentlessly, and when space-time is curved near a massive object, that steady march through the time dimension gets bent. The straightest path through curved space-time, the path of zero force, the geodesic, happens to look, from our perspective, like falling toward the Earth. The apple doesn't fall from the tree because a force pulls it. The apple falls because it's following the straightest available line through the curved space-time near the Earth. And that straight line, traced out through the spatial dimensions, curves toward the ground. The apple is coasting freely, naturally, the way a ball rolls along a curved track with no engine pushing it. Meanwhile, you sitting in your chair are not following a geodesic. The floor is in the way. The electromagnetic forces between the atoms in the ground and the atoms in your shoes are shoving you off the natural path. That push, that forced deviation from free fall, is what you feel as weight. It isn't gravity pulling you down. It's the ground pushing you up. You're being accelerated away from the path you'd naturally take. And suddenly, the equivalence principle makes perfect sense. The person in the accelerating rocket and the person standing on Earth feel identical things because they are in identical situations. Both are being pushed off the natural free-fall path. The rocket does it with engines. The ground does it with the rigidity of solid matter. The result is the same because the physics is the same. There is no gravitational force to distinguish them because there is no gravitational force. Now I should be careful. When I say there's no gravitational force, I mean there's no force in Newton's sense, no invisible hand reaching across space. There is, however, curvature. The curvature is real. The effects of curvature, the way paths converge, the way objects approach each other, those are real. We just shouldn't call it a force. It's geometry, the shape of the stage on which everything moves. John Wheeler, a brilliant physicist and a wonderful human being, once summarized the whole thing in a single sentence. Space-time tells matter how to move. Matter tells space-time how to curve. That's it. That's all of general relativity in plain English. Mass and energy warp the geometry of space-time, and objects then follow the straightest paths through that warped geometry. No force required. Let me give you a picture that might help. Imagine a large rubber sheet stretched flat and taut. Place a heavy bowling ball in the center. The sheet sags and bends. Now roll a marble across the sheet. The marble doesn't travel in a straight line. It curves toward the bowling ball. Not because the bowling ball reached out and grabbed it. The marble is simply following the shape of the surface. I should warn you, this analogy is imperfect. The real thing is four-dimensional and involves time in a way the rubber sheet doesn't capture. But the essential idea is right. The curvature does the work. No force needed. Let me try to make the geodesic idea even clearer. A A geodesic is simply the straightest possible path through curved space. On a flat surface, the straightest path between 2 points is a straight line. On a curved surface, the straightest path might look bent to someone watching from outside, but it's the best you can do given the geometry. When airplanes fly from New York to London, they don't follow a straight line on a flat map. They fly a great circle route over the North Atlantic, which looks curved on the map but is actually the shortest, straightest path on the curved surface of the Earth. Nobody is pulling the plane north. The geometry makes that the natural path. Space-time geodesics work exactly the same way. A ball tossed across a room follows a parabolic arc. Newton says gravity is pulling it downward while it moves forward. Einstein says no, the ball is tracing a geodesic through curved space-time. If you could see the full four-dimensional path, rather than just its shadow projected onto three-dimensional space, you'd see that it's the straightest line available in that region of space-time. The parabola is what that straight four-dimensional path looks like when you squash it down to 3 dimensions. You're looking at the shadow of the real thing. The shadow is curved, but the path itself is straight. The moon orbiting the Earth is doing the same thing. It's not being held on a leash by some gravitational force. It's moving in a straight line through the curved space-time surrounding the Earth, and that straight line projected into our spatial picture looks like an ellipse. The moon is coasting. No engine, no rope, no force, just geometry. This also solves the problem that tormented Newton. In his picture, gravity acts instantaneously across any distance. In Einstein's picture, there's no such problem. Curvature is a local property of space-time. A passing object responds to the curvature right where it is, not to some distant mass far away. If the sun were to suddenly vanish, the change in space-time curvature would propagate outward at the speed of light. The Earth would continue in its orbit for about 8 minutes, the same time it takes light to travel from the sun, and only then would the change arrive. No magic, no action at a distance, just geometry rippling outward at the speed of light. Einstein published General Relativity in November 1915. Immediately, it made 3 predictions that Newton's theory couldn't. First, the orbit of Mercury. Mercury's orbit is an ellipse, but the ellipse itself slowly rotates around the sun. The point of closest approach shifts a tiny amount each orbit. Newton's theory could explain most of this by considering the gravitational pull of the other planets, but it came up short by exactly 43 arcseconds per century. Sounds like almost nothing, but it had puzzled astronomers for decades and nobody could account for it. Einstein's curved spacetime predicted exactly 43 arcseconds per century, right on the nose, no adjustments, no fudging. When Einstein finished that calculation, he said his heart palpitated. He was beside himself with joy for days. Second, the bending of light. If spacetime is curved near a massive object, then light, which also follows geodesics, should bend when it passes close to the sun. Newton's theory also predicted some bending, treating light as particles affected by gravity, but it predicted only half as much as Einstein did. In 1919, during a solar eclipse, Arthur Eddington measured the positions of stars near the edge of the sun and found their light was deflected by exactly the amount Einstein predicted, twice the Newtonian value. The newspapers went wild. Einstein became famous overnight. Third, the slowing of time. Clocks in stronger gravitational fields tick more slowly than clocks in weaker ones. This is not a mechanical effect. It's not that the gears slow down. Time itself flows at different rates depending on the curvature of space-time. A clock on the ground floor of a building ticks slower than one on the top floor. The difference is extraordinarily tiny, but it's real, and it's been measured. In 1959, Pound and Rebka sent gamma rays up a tower about 22 meters tall at Harvard and measured the frequency shift caused by the difference in gravitational potential between top and bottom. The result matched Einstein's prediction exactly. Time genuinely runs slower closer to the Earth. Any navigation system relying on precise timing from orbiting satellites has to account for this effect, or it drifts by kilometers per day. If gravity were just a force pulling things down, there'd be no reason for clocks to run at different speeds. But if gravity is the curvature of spacetime, and spacetime includes time, then of course time is affected. The curvature distorts time just as it distorts space. Now I can anticipate the objection. If this is all so clear, why does everyone still talk about gravity as a force? Why do teachers still draw arrows pointing down? Because Newton's picture works beautifully for everyday calculations. Treating gravity as a force gives you the right answer for almost everything you'd ever want to compute. The corrections from Einstein are incredibly small unless you're near something extremely massive, moving very fast, or demanding extraordinary precision. For engineering, architecture, launching rockets, Newton is more than adequate, but practical and convenient isn't the same as true. A flat map of the world is practical and convenient, but Greenland isn't actually the size of Africa. The flat map is useful, but it's wrong about the geometry. Newton's gravity is the flat map. Einstein's curved spacetime is the globe. Near a black hole, where spacetime curvature is extreme, Newton's picture gives nonsense. At the surface of a neutron star, Newton is wildly off. For the universe as a whole, the expansion of space, the Big Bang, the ultimate fate of everything, you need Einstein. The flat map doesn't work anymore. Let me bring this back to you sitting in that chair. Feel this. Don't just understand it. You feel a force right now. That force is real, but it's not gravity pulling you down. It's the chair pushing you up. The atoms in the chair, bound together by electromagnetic forces, are resisting compression. They're pushing against your body, accelerating you upward, away from the geodesic you'd naturally follow. Your natural path, the path of zero force, would take you straight down through the floor, through the earth, following the curves of space-time. The ground prevents that. The ground is what's acting on you, not gravity. In a very real sense, you are being held up against your will. The natural state, the state of pure freedom, is free fall, weightlessness, floating. The astronaut in orbit is freer than you are. Nobody is pushing the astronaut. Nobody is acting on the astronaut at all. The astronaut follows the straightest available path through space-time, and that path happens to loop around the Earth, and the astronaut feels nothing, zero force, perfect peace. You sitting in your chair are being continuously shoved. Every second, the electromagnetic forces in the floor accelerate you upward. You've felt that your whole life, and because you've felt it your whole life, you assumed something was pulling you down rather than something pushing you up. You had the direction of the force backwards. You had the cause backwards. The most familiar sensation in your life, the press of your own weight, was misidentified. This is one of the deepest ideas in all of physics, and there's something even more disorienting buried in it. Why does Earth's mass curve space-time? How does a lump of iron and rock bend the fabric of the universe? Here we hit the edge of what simple language can carry, but let me try. Einstein's field equations, 10 interlocking equations published in 1915, tell you exactly how mass and energy determine space-time curvature. They're ferociously complicated to solve. But the core idea is stunningly simple. Wherever energy is present, space-time responds. Not just mass, energy of every kind, pressure, stress, momentum, all of it shapes the geometry. And here's something that should stop you cold. That geometry isn't just a passive backdrop, it's dynamic. It changes, it ripples. When two massive objects orbit each other, they shake the fabric of space-time. And those shakes travel outward as gravitational waves, ripples in the geometry of the universe itself. Einstein predicted them. And crucially, these waves aren't waves traveling through space-time the way sound travels through air. They are waves of space-time. The medium itself is waving. Space stretches in one direction and compresses in another, oscillating back and forth. The distance between objects changes not because the objects move through space, but because the space between them expands and contracts. That only makes sense if gravity is geometry. If gravity were an ordinary force, it would shake the actors on the stage. Gravity shakes the stage because gravity is the stage. These waves should be passing through us right now, constantly, from violent events scattered across the cosmos. We can't feel them. They're unimaginably weak by the time they reach us, but they're there. The fabric of space-time perpetually trembling, each ripple encoding information about some collision or catastrophe in the distant universe. There's another consequence I find especially wonderful. If space-time curvature replaces gravitational force, then the force of gravity has no strength at all. There is no force. There is only geometry, and geometry doesn't exert effort. A curved surface doesn't try to be curved, it simply is curved. Objects follow those curves because that's what straight lines look like in a curved space. When you pick up a heavy suitcase and feel the strain, you're not fighting gravity. You're fighting the electromagnetic forces in your own muscles and bones that are accelerating the suitcase upward. The suitcase, if you let go, would follow its geodesic, its natural straight path through curved space-time, and it would fall. And falling requires zero force. The effort, the strain is entirely yours. Space-time just sits there, curved and serene, and anything you do to deviate from its geometry costs you energy. This is a total inversion of the ordinary picture. Instead of gravity being the force that makes things happen, gravity is the absence of force. Free fall is inertial motion. Sitting in a chair is the accelerated state. Down isn't a direction gravity pulls you. Down is the direction you're being pushed away from. There's one more thing I want to tell you, and it's perhaps the strangest of all. We said clocks run slower in stronger curvature. There's a beautiful way to connect this directly to why things fall. Everything is moving through time right now. You're moving through time as I speak. Near Earth's surface, time runs slightly slower closer to the ground and slightly faster higher up. An object sitting still in space, but moving forward through time will naturally drift toward the region where time flows more slowly. Not because a force pulls it, but because the straightest path through space-time, when time flows at different rates at different heights, curves in the spatial direction toward the ground. The object is just trying to go straight, and the warping of time bends its path downward. Here's what's astonishing about that. Objects fall toward the Earth largely because of the curvature of time, not the curvature of space. For everyday situations, the spatial curvature near Earth is actually tiny compared to the time curvature. The main reason the apple drops from the tree is that time flows slightly slower at the base of the tree than at the top, and the apple, following the straightest path through that temporally uneven landscape, drifts downward. Gravity, the thing you feel pulling you to the ground, is mostly about time. Let me give you an image for this. Imagine two hikers walking side by side through a field. They both move at the same speed, both pointing straight ahead. But the ground on one side is muddy and the other side is firm. The hiker in the mud covers less distance per step. Even though both are aimed directly forward, the pair gradually curves toward the slow side, toward the mud. No force is pulling them. It's just that one side produces less forward progress, and the pair naturally veers that direction. Now replace the hikers with the top and bottom of a falling apple, and replace ground speed with the rate at which time passes. The bottom of the apple, slightly closer to Earth, is in a region where time flows a little more slowly. The top, slightly farther away, is where time flows a little faster. The apple, moving forward through time as everything does, finds its bottom making slightly less progress per moment than its top. That difference, that gradient in the flow of time, bends the apple's path in the direction we call down. No force, no pull, just uneven time. If time flowed at exactly the same rate everywhere near the Earth, nothing would fall. Everything would float. The whole drama of falling, of weight, of orbits, is largely a consequence of clocks ticking at different rates at different heights. I don't know how that makes you feel, but it makes me feel dizzy in the best possible way, because it means the universe is wilder, stranger, and more beautiful than the simple picture of a force reaching out and yanking things around. There is no yanking, there is only shape, the shape of space-time, the shape of reality itself. Newton gave us something magnificent, and I would never diminish it. His law of gravitation opened the universe to calculation. It launched the scientific revolution, predicted planets, sent people to the moon. As a tool, it's one of the greatest achievements in the history of the human mind. But it's a map, not the territory. The territory is curved space-time. The territory is a universe where falling is freedom, standing still is being pushed, and geometry, the shape of space and time, guides every particle, every photon, every galaxy along the straightest paths the curvature allows. So the next time you feel your weight in a chair or watch a ball roll off a table, pause for just a moment and think about what's actually going on. Nobody is pulling that ball down. The ball is free. You are the one being pushed up. The ground, this thin shell of solid rock floating on a sea of molten iron, pressing against the soles of your feet, accelerating you away from the path you'd naturally follow. You are under a force. The ball is just going straight. I know this is hard to accept. It goes against every instinct. But physics doesn't care about your instincts. Physics cares about what's true. And the truth, confirmed by every experiment we've thrown at it for over a century, is that gravity is not a force. Gravity is the shape of the road, and everything, including you, is just trying to take the straightest path available. And I'll leave you with one question to carry home. If gravity is curvature, if mass and energy bend space-time, fine, we can accept that, we've seen the evidence. But how? By what mechanism does a lump of matter reach out and reshape the fabric of space and time? Einstein's equations describe the relationship with breathtaking precision. They tell you exactly how much curvature a given amount of energy produces, but they don't tell you why. The underlying mechanism remains as mysterious today as Newton's action at a distance was 300 years ago. We traded one puzzle for a deeper one, and I think that's exactly what genuine progress in physics looks like. You don't eliminate the mystery. You push it down to a more fundamental level. You swap a shallow puzzle for a profound one, and then you keep going. There's something humbling in all of this, if you let it in. For 3 centuries, the finest minds in physics worked with a picture of gravity that was, at its root, incomplete. Not because they were careless, not because they lacked imagination, but because the right answer was so alien to everyday experience that nobody could have found it without being pushed there by relentless logic and stubborn experiment. Newton's gravity was obvious. Einstein's gravity is true. And the distance between obvious and true, that gap is where all the good physics lives. I sometimes think about Einstein sitting in that patent office in Bern, processing other people's inventions, when the idea of the equivalence principle struck him. A man falls freely. He does not feel his weight. A child could understand that sentence. And yet from that seed grew an entirely new conception of space, time, and the universe. It took another 8 years to work out the mathematics, which nearly destroyed him. He had to learn tensor calculus from scratch, invent new geometric tools, stumble through years of wrong turns. But the core insight was a single physical observation stated in plain language, and it was correct. That's the kind of thinking I admire most in physics. Not the mathematics alone, though the mathematics is essential. Not the experiments alone, though they're what keep us honest. But the willingness to take a simple observation, follow it wherever it leads without flinching, and accept what it tells you. Even when what it tells you is that the floor is pushing you up and the falling apple is the free one. So tell me, now that you know the ground is shoving you upward and nothing is pulling you down, does the world feel any different to you? Because I find myself genuinely curious what that does to a person, hearing it for the first time.